Hello, and welcome to the 3D Printing for the Future event. In the next 4 days, we've got a lot of interesting topics where we're going to not only talk about where 3D is going in the future, but also discuss the implications that that could have on sustainability, on innovation, and talent of the future. My name is Ed Davis. I'm the Strategic Director for Digital Manufacturing in the Office of the CTO at HP. I'm going to be kicking off this event, and I'm going to be setting the context for the next 4 days and tying together what 3D printing can do today to the megatrends, and then extrapolating out into the future where 3D printing will be in the far future, along with how 3D design needs to change as 3D printing evolves. So let's go ahead and get started and start the presentation. If you could just advance to the first slide, that'd be perfect. So first, 3D printing has been around for a long time. It's been around for now more than 3 decades, and it's been mostly relegated to concept prototyping. Most of the 3D printers up until now have been used in concept prototyping, and there's a reason for this. And the reason is that most 3D printers up until now do not provide the consistency of mechanical properties and accuracy or dimensional tolerance that are necessary to address the use cases that are below that dotted line. All the use cases from functional prototyping all the way down to hybrid supply chain that I'll be discussing at a later portion in this presentation. Now, there's a reason for this, this challenge, and I'll describe this in the following slide. Now, to describe this, what I'm showing here is an oversimplification of the product development process. And in this oversimplification, you've got the design phase, you've got the development phase, you've got the production phase. And I've highlighted the development phase in blue for a very specific reason, and it's to also renege a fallacy that's happened in the 3D print industry, which you all have heard in probably other events, that you can go directly. The beauty of 3D printing is you can go directly from design to production. The fact is, if you have quality requirements, part consistency requirements, you cannot skip that development phase. You have to develop and validate that the part and the process together have the consistency of properties that you're looking for. In that development phase, the people on the design side, the people who are demanding parts over on the left-hand side, have to design the parts to the process that they have in mind. And the people over on the right-hand side who are supplying the parts need to tune the process to the specific part. And there's a reason for this. And the reason is physics. And the reason is explained in the following slide. So the physics of thermal processes, and I'm talking specifically thermoplastic right now, but this applies to all thermal processes, is that the part quality is both a function of the thermal history, which is a function of both the part geometry and the process settings. There's an interdependency between the design and the process settings. And very specifically, the dimensional error is tied to that thermal history of that part, which is tied to the thermal stress within that part, which is also a function of both the design and the process settings. And to clarify very specifically, if you have a small feature in a design next to a large thermal mass, the large thermal mass will heat up and cool down differently than the small feature, and there will be a thermal stress between those two details in the design, and that will cause dimensional error. So very specifically, this interdependency between design and process is why you have to go through a development and validation phase. Whether it's injection molding or whether it's 3D printing, you have to go through these phases if you want to tune the process to the quality requirements of the design. So then in the next slide, I'll show specifically what HP is doing to address this. Is on the design side, on the demand side, we both have an MJF MJF stands for Multi-Jet Fusion Design Handbook, which you can get online for free, or we offer a professional service for design for manufacture so that you can tune the design with the guidelines of MJF in mind. And then on the right-hand side, we have introduced a process control software that allows the process engineer to tune the batch settings to the specific part and batch that you have in mind. Using those two together, you go through this development phase, and then you can go into production with our production systems. Now, what that enables a person to achieve, both the design and the supply side guy, it allows them to achieve a consistency of accuracy that we describe in the following slide. There is an international tolerance for an international tolerance grade for it's a standard for explaining what dimensional errors are possible. The first thing to note is that the small number is better than the large number, and very specifically, if we go to the next slide, I'll show you the relationship. This is an international standard. It's both an ISO and an ANSI standard. If you go to the next slide, please. What you see is that this this relationship on the horizontal axis, you see the dimensions length. On the vertical axis, you see what error is acceptable, and what you see is an asymptotic relationship between the dimensional error and the length of the dimension. Now, people often ask, what's a good dimension to achieve for a multi-part mechanism? And I often look at the 400 millimeter error, and that's quite a large error if you go to IT15. What you see is as you go to IT13, IT12, IT11, the number actually starts to approach each other. And so generally speaking, for multi-dimension mechanisms, you're looking for an IT13 or better to have good interaction between the different parts in a mechanism. So if you go to the next slide, what we've been able to achieve with this process control software and following the design guidelines is the following. What you generally find with the typical injection molding is that a highly precise mold will get you anywhere between 8 and 11 on this IT scale, which is phenomenal. It's actually very, very good tolerance. To get better tolerances, you have to machine it. A normal mold will get you 11, 12 on this scale with a CPK of 1.33. Typical 3D processes are in the range of 15, 16, 17. And actually, aluminum molds are generally 14, 15, 16. And so, as you see, typical 3D processes are far to the right on the scale. With our process control software and following the design guidelines, and using the latest model 5200 to produce the parts, we're able to achieve an IT13 on the X and Y axes, and a little bit worse in the Z axis because the resolution is lower in the Z axis. So what we're actually able to achieve is more direct competition with typical injection molds. So what that allows a person to do then is open up the use cases beyond concept prototyping. And what this means to a program manager, I'll explain in the next slide. The program manager is typically a hardware program manager, whether you're a program manager for an automobile, or whether you're a program manager for a printer, or you're a program manager for any other device. What you're typically trying to do is balance the scope, the schedule, and the investments or resources to optimize the return on investment. Now, the scope is the functionality of your product, and it needs to be different than the competition, and it should be different than your previous version of the same product. Schedule, of course, is time, and then investment is literally the money that you put into resources or other investments. So let's focus down into this program manager's world by going to the next slide. And what I want to focus down is to think about how they balance investments versus cost. Now, there's a fallacy in the 3D print industry, and there's this typical break-even curve that you see here. The horizontal axis is the total quantity of parts produced, for example, per year. The vertical axis is the total cost of those parts. And so the story goes in the 3D industry. If you were to, for example, pay $20,000 for an injection mold, and you were only going to make one part, well, then that part would cost you $20,000 plus maybe two, so $20,002. However, if you're going to make 1,000 parts, well, it starts to go down and approach that $2 range. And if you're going to make 100,000, well, it gets closer and closer to $2. And so that's the typical curve that they show for injection molding. Now, for 3D printing, they tell you the following story. If you advance to the next slide, please. They tell you that regardless of whether you're printing one part or two parts or 1,000 parts, the parts cost the same. That's not true. What I just explained is that you have to go through a development and validation phase, even with 3D printing. You need to at least set up the quality processes for your 3D printer. Setting up the quality processes means programming a CMM to measure the parts, developing a holder in place while the thing measures things. It's going to cost you probably $1,000 or $2,000 just to set up the quality processes. So if you're going to make only one part and have quality requirements, well, it's going to cost you $2,000 plus the cost of the part. And so there's always an upfront cost. There's always a setup cost. There's no such thing as a straight line unless you skip that development phase, which you should not do unless you don't have quality requirements. A bigger problem with this curve, though, and what they say is, look, if you hit that break-even point, less than that break-even point, you should 3D print. A worse problem is shown in the following slide, which is that many 3D processes are very expensive and don't produce that many parts. And so, for example, if you were going to produce parts with a laser sintering machine, and that laser sintering machine could produce 2,000 parts a year, if your production quantity per year was 10,000, then you have to buy 5 laser sintering machines that cost about $300,000 a piece, and dedicate those to that part. That's $1.5 million. There's no break even. You better buy a $20,000 mold, because the $20,000 mold is a lot less expensive than 5 laser sintering machines. So the problem with this kind of break even story is the bad ratio of productivity divided by acquisition cost for most 3D print processes up until today, where we have processes like multi-jet fusion, which are actually quite productive. Now, the thing I really don't like about this break-even story is that this is not how program managers generally do accounting. So if we go to the next slide, I'll show you how program managers generally do accounting. Is you've got upfront costs over on the left-hand side, and that's your return on investment. And then you introduce the product, and you have a P&L, a profit and loss statement for that product line, and the part cost is part of the loss of the P&L. So the story goes, if you go to the next slide, the story goes in this break even that you pay a lot for the mold, and as a result, you pay very little for the molded part over on the right-hand side. And 3D printing, you pay nothing for upfront development, but the thing costs you 10 times more. This whole argument falls apart for the program manager. If I'm the program manager on the BMW Model 3, my Model 3 needs to compete with the Mercedes C-Class. I cannot charge the customer 10 times more money for the Model 3 just because I didn't invest in tooling. the cost on the right-hand side has to be comparable for the program manager. And he doesn't care about, trying to bury the investment cost into that. It has to be cost competitive. But the fact is that this is not really how the situation looks. If you go to the next slide, what really happens is that you can do the process tuning like with this process control software, which takes a little bit of investment on the right-hand side, but it reduces the part cost on the right-hand side. And if you go to the next slide, you can follow the design rules for process and improve the quality even further. It requires more investment on the left side, but you reduce the cost even further. You can apply, in the next slide, you can apply material reduction through generative design topology optimization and reduce that cost even further. Or if you go to the next slide, you can do slight changes to the design so that you can fit more into a batch. For example, on that picture that's shown there, if that stack of parts were square instead of angled, you could only fit so many in a batch. But by putting a slight angle, you can fit more into the batch. So the batch, in fact, is the primary cost. And so you start to approach the cost of that injection molded part by applying all of these techniques. But oftentimes, what will happen, oftentimes, the cost efficiencies of injection molding are phenomenal. So oftentimes, your 3D printed part will still cost 2 or 3 times more than the injection molded cost, with one exception, which is shown in the following slide. When you have a design like this, and this is a real design in our 3D printers, what it is an airflow system to keep the pens cool while we're printing. It's actually shown upside down, but when we turned it into moldable parts, we had to break it into parts which could be molded, which ended up being 6 parts plus assembly. If you 3D print it, you can print it out as 1 part without further assembly, and that really optimizes the cost. And then furthermore, we took that same design, and our friends at Siemens helped us optimize the airflow through that system so that it actually has higher performance than the original version or the middle version. And so the fact here is that not only can you do cost optimization, but you can do a higher performing thing. So if you go to the next slide and you compare this integration of several parts to the cost of several injection molded parts plus assembly, in fact, it's more cost effective to use the 3D printed version. So then, what can a program manager do with this information? If we go to the next, let's focus now on a story of investment versus time. If you could advance, please. So go ahead, one more. All right, so here on the left-hand side, the vertical axis going down is your investments. And on the right-hand side, the vertical axis going up, you could consider your profit or your revenue. And then the horizontal axis is time. So what happens in hardware program development, each phase of hardware program development costs more and more money. Initially, you're just doing prototyping, and then you start to launch tools, and then you rent a factory, and then you buy assembly line tools, and then you're paying the factory workers. Every phase of hardware development gets more and more expensive until you finally introduce the product, stabilize the design, and then you're down to a kind of a lower level manufacturing overhead. And then you sell the product through its useful competitive life. All right. And then you can think of this graph as return over investment, right? Now, if you go to the next slide, there is a serious concern in a program manager's mind when you're near the introduction of a product and you've got a technical issue and you need to delay. What ends up happening is that your investment profile continues at the high rate. You don't go back to zero. You continue paying for everything that you're paying for until you solve that problem. Furthermore, up at the top, when you start to delay, if you go to the next slide, what happens is that your return profile is actually shortened. You don't lose the ramp, you shorten the competitive useful life of your product. Mercedes is not waiting for BMW to solve their problems. And so the competitive life of your product becomes shorter. If you recalculate the return on investment at that point, you may actually come to the conclusion that it's a bad return on investment. Of course, you always convince yourself it's better to keep going than to start all over. You do some accounting games. And so what 3D printing can do, if you go to the next slide, is actually enable that program manager to keep that schedule on track through strategies like bridge manufacturing, which we'll describe in the next section. If you go to the next slide. Now we're going to skip through. Let me just go to the next slide right away. So with 3D printing, what do you get? You still go through a development and validation cycle, but it's much shorter than the cycle that you would go through if you were injection molding the same part. And so in case of 3D printing, you can do that development and validation time in a week, maybe 2. With injection molding, depending on the complexity of the mold, it could take you 10 weeks, could take you 20 weeks. And so what you get with 3D printing is actually a shorter development and validation phase, which then should allow you the following benefits. If you go to the next slide, what you get then is less time, less investment during the development phase, a slightly longer production phase. And then at the end of life, this is how end of life parts are generally managed. When that BMW Model 3 is obsoleted, BMW does not keep producing on a monthly basis spare parts. What they do, generally speaking, is they do a lifetime buy of spare parts, and they put those spare parts in inventory around the world in case that BMW, which they just obsoleted, breaks in the next 10 or 15 years. They still support their customers that just bought that last of a model year. And so there's a lot of money stuck in end of life parts inventory. So the good thing with 3D printing is you can print those out when you need them. You don't need to build up a big inventory. Now, unfortunately, in a car, an automobile, most of the parts, it's going to make sense financially to injection mold them. So this is not a real scenario for most parts in the BMW Model 3. If you go to the next slide, this is a more realistic scenario. A more realistic scenario is that there's some parts that make sense to 3D print. And for those, you have, they are not the critical path to introduction. And then for many of the plastic parts, it's going to actually make sense to injection mold them. And that most likely is the critical path to introduction. And so the 3D printed version, or the 3D printed parts, can actually go through more iterations because they have more time to do those iterations and not only have higher performance, but higher quality at the introduction date. But we're all waiting to hear about bridge manufacturing. So let's go to the next slide and say, what do you do with bridge manufacturing? Well, if this design were unstable, I would not launch tools. If I launch tools and it's an unstable design, I'm likely to have to rework those tools or throw those tools away and start over. And so if I have an unstable design and I know it's unstable, I would continue to use 3D printing through the development phase, stabilize the design, start manufacturing with the 3D printing at the same time that I launch the molds. And when those molds are ready, switch production from 3D printing to the more cost-efficient injection molding. All right, this is bridge manufacturing. It's bridge manufacturing because you start with a type of manufacturing bridging to your final production method, which is most likely because it's more cost effective. So this is one reason for bridge manufacturing. In the next slide, there's kind of the opposite story, which is up on the top, you start with an injection molded version, you introduce the product, you find a catastrophic failure in the field. When you find that catastrophic failure in the field, what I mean by catastrophic failure, I mean a recall situation. I would argue that it makes more sense to develop and validate with 3D printing restart production to address the problem, and then switch back to injection molding at the end once that mold is ready. The final reason you may do bridge manufacturing is in the following slide, which is maybe important in today's situation, especially for small companies. You may not have money this fiscal year to continue paying for your tooling. So you can delay tooling decisions by bridge manufacturing as well. Now, if you develop and validate the 3D printed version, and then you develop and validate the injection molded version for this bridging strategy, why would you do end of life with the molded parts? You wouldn't. If you go to the next slide, what you would do is at the end of life, switch back to 3D printing so that you don't have to stick all those parts in inventory. And this leads us to the most complicated, which is hybrid resilient supply chain on the next slide, which is the following, where you intentionally develop and validate a 3D printed version and then develop and validate injection molded. Hybrid supply chain means that you're using two methods for production at the same time. If you look up the definition, it literally means you incorporate both a cost-effective method, which could be the injection molded, and an agile method, which is the 3D printed up at the top. Now, with this model, during normal production, what you would do is your push production, you would do through the cost-effective method, and your pull production, what I mean is on-demand production, you would do with 3D printing. And pull production could be spare parts, or it could be unforeseen forecasts. And in this way, in this hybrid, in fact, you get all the benefits of a pure pull production in that you only fabricate what's necessary. All right. And this leads us to the following slide. So what happens when you have supply chain disruptions? And I'll argue that this hybrid supply chain can help you with supply chain disruptions. For those of you who don't work in supply chain, disruptions happen all the time. We heard about it this year because COVID was a very big disruption, but there's always some level of disruption going on in the world, whether it's a tsunami in Thailand or a volcano in Iceland or a strike of the dock workers in Los Angeles. There's always some sort of disruption. So having this hybrid supply chain actually allows you to switch between supply on demand when these disruptions occur. Now, how we've used this in the case of COVID is shown in the following slide, and this I use to demonstrate how quickly you can get things done. When COVID hit in March, our 3D print team in Barcelona, they knew some people at the Hospital San Pau, and the hospital said, look, we're running out of face shields. Can you guys help us? And our team said, yeah, we probably can, but we never designed face shields before. So they met with the doctors on a Saturday afternoon, got the design requirements for the face shield. There's 3 requirements. It has to prevent splashing. It has to have optical clarity so the doctor can see what he's doing. And then all of the parts need to pass an impact test. And so they got the requirements from the doctors, came up with the first design, printed it out, had it ready for Monday morning, reviewed the design with the doctor. They went through, I think, 6 iterations throughout the week. By the end of the week, they had passed the requirements. So they went through the development and validation in 1 week. And then they started printing out these face shields for the doctors in the hospital in San Pau. At the same time, we uploaded our design to the internet, and a lot of our customers, our partners, started printing them for their local hospitals. So this is a description of what do we mean by supply chain disruption? How do you deal with that? 1 week development and validation, immediate distribution because it's digital. Now, if you go to the next slide, just to illustrate, if you're gonna build millions and millions of these, it's going to make sense to buy a mold for these plastic parts shown in that headset. But I would argue that you want to keep both designs around. You want to, in this case, have a hybrid supply chain and have the 3D printed version in the case of disruptions so that you don't have to deal with lack of face shields. So moving on to the next, the value of 3D printing then is not to replace injection molding, it's to complement injection molding, either because you have higher value parts or customization needs, or because you want this flexibility in the supply chain. And those are like two different reasons for using 3D printing: to complement injection molding, not to take the place of it. Now let's talk about the future, going to the next slide. So we're going to go through several topics. I'm going to talk through one at a time. I'm going to do a little bit of level setting just to make sure everybody's on the same page. And so we're going to start with megatrends. If you go to the next slide, megatrends is not an HP term. They are the major macro trends that are happening in the world. And you can Google these. There's companies that do research on these megatrends. HP does their own research, and we do our own research for the following reason. If you go to the next slide, because we intend to be in business 10 years from now, 20 years from now, we're looking to understand the megatrends, to understand what sort of talent we need to acquire or develop. What are the processes and tools of the future? Who are our customers in the future? What are they looking for? And what are the new business models? So we're doing this analysis. It's actually available online. Our analysis is available for free online. I think we've got the links at the end. We do it for ourselves because we're trying to stay on top of these trends for our own sake. Now, in the next slide, HP breaks these megatrends into these four major categories because we have determined that these four major categories are the most important for our business. And then we break it into these sub-themes shown below each of the columns. I'm not going to go through this in boring detail, but rapid urbanization is, in fact, the movement of people towards where the jobs are. And I don't mean necessarily that people are moving to the middle of the city. What I mean is people move where the jobs are. And if the jobs are in Los Angeles County, people will be moving to Los Angeles County. Changing demographics, this is just the aging population. What's going on is that there's less than 2 children per couple in most of the developed world. So that on average, the age of the population is going up. Hyperglobalization, I prefer to call hyperconnectivity, and then accelerated innovation is exactly what that means. Now, what I've highlighted in blue are the topics that I intend to put together in a story that I'm going to tell at the end. The only thing that I hope is that everybody believes that the world is becoming automated, because that's a key to the story making sense. If we go to the next slide, to emphasize this automation, I want to talk about Industry 4.0 and clarify some terms. Industry 4.0 is the use of the data across the entire product life cycle to make that entire product life cycle more efficient. It is broader than Manufacturing 4.0. Manufacturing 4.0 could be thought of as the smart factory. Manufacturing 4.0 is using the data in manufacturing to make manufacturing more effective and efficient. Now, 3D printing does not need to be an element of smart factories. It can be, but it's not necessary. For smart factories, you actually just need sensors and data. 3D printing can be a version of smart factory for parts. Now, to discuss automation, let me talk about Industry 4.0 just to make sure we're all on the same page. We'll go to the next slide. Here, I've broken the product life cycle into more phases than I previously had. I've given product development just one bubble because I didn't need to emphasize it. And then I gave manufacturing 4 bubbles: part production, subsystem assembly, top-level assembly, and distribution. Those 4 are what's considered manufacturing. Those 4 could be Manufacturing 4.0. But then you sell the product, and you install the product, and the customer uses the product, and you repair the product, and you replace the product. That is the entire product life cycle. Industry 4.0 has that full breadth. Now, the way that this looks, it's like a perfect digital thread all the way across all of these bubbles, right? That's not reality. What reality is shown in the following slide. Reality is that, generally speaking, if you go to the next slide, please. Generally speaking, product development is done in one company in one country. All this manufacturing is generally done in other companies in other countries. And what literally happens is that the information in product development is transferred to all of these manufacturing bubbles through an email, and through these little people that are running from bubble to bubble. Those are little people getting on airplanes and going to this other country and explaining the email. And so the information flow going from the left to the right tends to have a delay. I would say that the average delay is several days, or maybe a week, maybe two. And so information flow, real information flow, going left to right. One, it's not a digital thread, it's emails and people. And two, it's kind of slow. There's a worse situation shown in the next slide, which is if you're one of these repair guys over on the right-hand side and you find a new problem in the field and you need to find the root cause, you have to go backwards through that value delivery chain and understand what happened. Did something happen wrong in distribution? Did something happen wrong in assembly? Were the parts not correct? Did you find the problem in R&D, but you ignored it somehow? Did the customer use the product in such a way you had not anticipated, and that caused a new failure mode? There's all these possibilities. The information flow going right to left is as bad as the information flow going right to left. So to fix that, in the next slide, what Industry 4.0 pretends to do is, one, you got to get all the information in a database, and then at the bottom, you need to apply data analytics to look for correlations between things, and then to inform people that they need to make decisions. It does not take the place of the people making decisions, but it helps them understand, I seem to have found a problem in the field was related to your part quality, you need to take action, right? So Industry 4.0 is pretending then to automate the correlation of data across this entire product lifecycle. And it's better shown actually in the next slide, which is that the idea of Industry 4.0 is that you're always monitoring all the data in that product lifecycle to always provide real-time feedback to all of the bubbles in that. And that data analytics that we showed at the bottom of the previous slide is actually the center. They're digital twins. They're virtual versions of the same system. So then what can you do when parts are digital? If you go to the next slide, if the parts are digital, then go ahead and advance. What is a digital part? Go to the next slide, please. When we introduced, if you could advance one slide, please. When we introduced the technology years ago, we talked about voxel control. We talked about being able to manipulate properties on a dot-by-dot basis. And we did that because, in fact, we've got a dot-by-dot process. And our strategy still is, in the long term, voxel control. But one of the things you can do with voxel control, if you go to the next slide, is if, in fact, you had metallic inks, you can start to embed sensors into mechanical parts. And if you go to the next slide, you could go and embed more than sensors. You can embed electronics. And so this then would be a real digital part. Not only is the product digital, but the part itself is digital. So what happened with this voxel control story, let's go to the next slide, is the following. We don't talk a lot about voxel control anymore, even though it's the long-term strategy, because it's first important to get in manufacturing. Because if you're not clearly in manufacturing of parts, then voxel control is kind of academically interesting, but not otherwise interesting. What I mean to say is, why would you prototype the embedding of electronics into a mechanical part if I could not produce those parts in the volumes and at the cost that I was interested in? So we focus now our conversation on getting into manufacturing, although the long-term plan still is to get all this voxel control, including the embedding of electronics into parts. So in the next slide, what you heard also when we introduced the technology, you can still Google this. I think it's still on YouTube. We showed a visionary video of, in the long term, what you can do is print out something as complicated as this electromechanical robotic chameleon without further assembly. Now, there's a couple of challenges for making this vision a reality. The first is that we need to invent all of this voxel control, all of these agents, all of this chemistry. It requires a lot of innovation. And so that's going to take us some time. But the other thing that needs to change is, if we could print this out without further assembly, how would you possibly design it? Would you say, point number one, voxel number one has this mechanical property, this electrical property, this color, this texture? Voxel, you can't do voxel by voxel design. It would take you forever to do this. And so what has to evolve is the design tools need to evolve towards what's called a generative design tool, which I'll describe in the next slide. The general design process is, if you could go to the next slide, please. The general design process is the engineer sets the design intent. I need a mechanism that does this, fits within this space, connects to the system here and here. And then the engineer goes to the CAD system, designs. And then they go to a simulation tool and simulate how well those designs meet the intent. And then they kind of go through iterations until they're happy. What happens in generative design in the next slide is the following, that the CAD tool and the simulation tool are integrated. And while the CAD tool, so the design engineer still sets the design intent, but this integrated design generative design and simulation tool designs options while simulating how well those options meet the design intent, and then presents the options back to the design engineer saying, look, I came up with these designs. Here's 10 options. Option 3, option 7 best meet your designs, but they're not perfect. And if you could reduce constraint number 5, I can do another iteration. This is automating the manual process of CAD and simulation. And the key is the integration of design and simulation. So how does this break up over time? This is the story I'm going to tell. All right, go to the next slide. In this, the horizontal axis is time. A lot of my slides, horizontal axis is time. The different columns are different eras of time. And for the sake of argument, everybody knows you don't go to sleep one day and you wake up the next day and you're in a different era. But for the sake of argument, let's pretend like they're distinct eras. The top row is what needs to change in design tools. The bottom row is what needs to change in print. And to explain the frame, I like to go all the way to the right. Smart products phase. All products are smart. Products talk to other products. Products repair themselves. Products design themselves. Products fabricate themselves. You could ask, what do humans do then? And I'll get to that in a minute. All right, so to get to that level of automation, let's focus on the top row. To get to that level of automation, in this hardware innovation phase, you have to have generative design tools, which are so perfect that they allow normal non-engineers to make something as complicated as electromechanical robotic chameleon without having safety issues, without the thing failing. The level of knowledge necessary, the level of multiphysics necessary for that level of simulation is a couple decades beyond our capability today. Even if we had the knowledge, the processing power for that level of simulation is a couple of decades away. And so to get to that level of automation, if you go to the tipping point for AM, what you need are generative design tools that allow professional engineers to do complex designs like that chameleon, and then they can test and validate. To get to that level, then you go to the design for AM phase, which is the beginning of generative design, where you could do something as complicated as remove material through this topology optimization that I'm showing with this in this little box here called changing what, or doing designs like this multiple densely spaced holes. Believe it or not, although multiple densely spaced holes sound simple, the current CAD tools, they bog down when you put a lot of small details into a part. And so many of the current CAD systems can't realistically handle something as complicated as small densely spaced holes. And then you're finally back into the first column, which is short run disruption. Jumping down to the bottom, then what we've introduced is a better, faster, less expensive way to make 3D printed parts. And so what we can do is change how people fabricate through these hybrid supply chains. We don't change what just yet, because one, the CAD tools don't allow it, and two, no supply chain manager in their right mind does not have assurance of supply. What I mean to say is, until there's a proliferation of multi-jet fusion factories around the world, you need a backup plan. And so there's two reasons why first you change what before changing, or first changing how you make things rather than changing what. Now what happens is that the printer is better than the design tool, and this puts creative tension on the design tool manufacturers. So they start making changes to the design tools to enter into this design for additive manufacturing phase, which then creates more demand for 3D printers, which facilitates this changing who, where, when things are fabricated. This who, where, when things are fabricated is what's called the re-engineering of the supply chain. And both this re-engineering of the supply chain and the evolution of the design tools are necessary to enter into that final phase, hardware innovation phase, which is not democratization of design phase, because now me and my friend, we can come up with a design, we can print it out at our local factory, we like it, we upload it to the internet, and if people like it, they buy it and they download their own digital right to one copy. And so in this hardware innovation phase, now it's as easy to innovate hardware as it is to innovate software today. So that leads us to then the final smart products phase. And what's left for humans? Now let me talk about talent just a little bit. What's left for humans, I will argue, in the long term is creative ability, is the ability to create things which cannot easily be programmed. And to get into this creative ability, I'll describe what I believe is like the ideal future talent. The ideal future talent has three elements: diverse knowledge base, a ability to learn fast and apply critical customer judgment, and tenacity. And you can think about this as you go into this hardware innovation phase. It's hyper innovation, it's hyper competitive. The more knowledge you have about not just mechanisms, but mechanisms, electronics, chemistry, programming, artificial intelligence, machine learning, the better off you are to come up with creative solutions. If you don't have all that knowledge yourself, you have to be with a team. Now, what I mean in this hardware innovation phase is really what I'm talking about is like the new Renaissance era. So not only are people scientific, but also artistic. Not just scientists, not just artists, but scientific artists like Michelangelo. And so first, diverse knowledge set. Second, critical customer judgment is necessary because things are so hyper competitive. You need to discount innovations which don't solve a real customer problem in a relevantly different way. And then to complement that, you need tenacity. What I mean by critical thinking is you need to kill bad ideas before you go too far. And tenacity is the opposite. Sometimes ideas don't take off just because of some timing, which is oftentimes not under your control, like macroeconomic conditions. So if you've applied your critical thinking to a customer problem and you believe that you have a strong differentiation for your innovation, you need to have tenacity to keep going, even if the world is telling you they're not ready yet. So that's my argument for talent. Now, this is long way out, like I say, probably a couple decades. How do we know the story is nearing the smart product phase? We know the story is near the end when you get to the following slide, when the following statement is true. When you can imagine and build things which cannot be designed and manufactured today, then you have arrived. Now, how the story begins is in the next slide. How the story begins is today, we can do hybrid manufacturing. If you go to the next slide, please. We can do hybrid manufacturing today, which allows us to match production to demand, which then in the next slide allows us to reduce our dependencies on inventories and warehouses, which puts creative tension on the design tools, which leads us to the next slide, which is then the design tools enable, if you go to the next slide, please. The design tools enable you to reduce the use of material through topology optimization, reducing the weight significantly, reducing the use of material significantly, which leads you to the next slide, which then allows you to waste less material and to improve cost. And if it's a lighter system, to reduce transport costs. And if it happens to be an automobile or something else, to actually reduce the energy in the use. This little multiple densely spaced holes, people say, what is that? One example of what you could do with multiple densely spaced holes are molded fiber molds. What is molded fiber? Molded fiber is a type of packaging that has been replacing polystyrene foam and packaging for a number of years. It's typical in these egg crates. Molded fiber is the material that this is made out of. To make this, in fact, you have to do a very, very manual process that I'll describe in a second. Well, our egg crate people, the people who are interested in molded fiber, no. If you go to the next slide, if you also look at the packaging, and the next slide, just go ahead and advance one more. If you look at the packaging in typical consumer electronics like PCs, a lot of times we have these end caps made out of polystyrene. HP has, part of our sustainability strategy, has a goal of replacing single-use plastic like this polystyrene foam, 75% of it by 2025. And so it's not just egg crates, it's actually a lot of packaging that currently or used to have polystyrene foam should start to be replaced with something that takes recycled paper products to turn it into paper pulp to make a packaging which is perfectly recyclable back into more packaging in the future. So now why aren't we going faster? Well, one of the reasons we're not going faster, shown in the next slide, is the following: that the process for making the screens for this molded fiber slurry to pass through is a manual process. I have a kind of a description here. If you look at something like this, what you do is you cut out a piece of, it's actually tighter meshes than this. I use this to illustrate. You cut out reliefs, you fold the thing into place, you pound it against the form, and then you stitch it back together. It's a very manual process. And you could imagine being so artisanal, it's not got a lot of quality control behind it. So what HP has done, we've now announced that we're going to be entering into the molded fiber tooling business, and you can Google HP molded fiber advanced tooling solution. We are taking orders for molded fiber molds that we will finish the design of the mold for you, print out the molds, and send you the molds. And so what we're trying to do is facilitate that more people than just HP can actually take this journey of replacing polystyrene. So then that leads us to the final. If you go to the next slide, the final is, and go one more, just skip right next to the next slide. when you can finally re-engineering supply chains, in fact, and you can do local production, not only do you reduce inventories and reduce warehouse dependencies, you also reduce shipping requirements, which then leads us to the summary slide in the next, which is all of the sustainability story for 3D printing includes all of these elements: the ability to reduce inventory, the ability to reduce shipping, using less material, having less waste, going towards a more fully recyclable world. And that's the summary for sustainability. Now, to close, let's go to the final slide, go to the next one. Let me go back to megatrends. I will argue that with this COVID situation, these megatrends have been emphasized and accelerated, that now that people have lost jobs, maybe in one part of the country, they will be moving towards where there's a job. Sometimes you have no choice, right? So the rapid movement towards where the jobs are will be accelerated by the current situation. The need for healthcare and digital health is being emphasized by COVID. Hyperglobalization is hyperconnectivity. You know, we're all doing virtual events these days. Of course, that's been accelerated. And then in the case of innovation in 3D printing, we're seeing the advantages of 3D printing for use in hybrid supply chains has been emphasized by the current situation of supply chain disruption. So I will argue that these megatrends not only will continue, they'll be emphasized by the situation that we've gone through in the past year. And that brings us to the final slide, where we've got some links for people if they're interested in more information. And now we have some time for questions and answers. And I think, Suzanne, you're gonna curate those questions for me.
Yeah. First question is, first of all, thank you very much, Ed. The first question is, it's more of a comment. An aspect not covered is to use 3D printing for the injection mold for conformal cooling and improved efficiency and to accelerate the mold build.
Yeah, yeah. You know, this presentation was kind of it was kind of made to talk about direct printing. There is the possibility to do printing of molds with generally with your metal processes. And in the case of printing with molds, there's actually a real specific advantage. You may actually be able, with this conforming cooling, to get better quality than you would get from a standard mold. Or alternatively, you may be able to accelerate the process time for the parts and maintain the quality, which then allows you to reduce the cost. So conforming cooling is a real use case for metal 3D print processes. That's correct. No denial.
Okay, I think we have time for just one more. And this question has to do with global climate change. Many believe that global climate change is the most pressing problem facing mankind. How is climate change going to affect megatrends? Yeah,
that's a good one. Actually, that's a darn good question. I haven't even contemplated it. I don't have a real direct answer, but what I think is that the column of innovation will be driven in part by this warming change. As an example, you know, how do we come up with this molded fiber as an example? The world has got to get rid of plastics that are floating around in the ocean. This is a clear opportunity. We first identified it internally, and then kind of innovated around it, and then decided to get into the molded fiber business. So I think what's going to happen is that the customer problem is global warming, and there will be opportunities to innovate around that. And because 3D printing is able to innovate more quickly, there actually are a lot of opportunities for 3D printing that I have yet to identify. I'd be interested in hearing people's ideas, because these new application areas are, of course, of vital interest to HP.
Great, Ed. Thank you so very much. We need to close. But thank you very much for your thoughts, and we will follow up with any questions that we couldn't get to directly with the folks who asked them. And thanks everybody to all the participants who joined.
Yeah,
Thanks
thanks
very
everybody.
much.
Thanks for taking the time. Hope to see you in the other sessions.